Math 287, Quest to College. I'm Joe Vasta, and we are covering section 5.2, orthogonal sets. Okay, so this is a little different than what we've heard. We know that two vectors are orthogonal if their inner product is 0. But what's an orthogonal set? Note in your homework that you want to skip 8, 19, 20. So look at our examples here. We have two sets, and it says, is the set of vectors orthogonal? So we don't know what that means, so we're going to need a definition. If yes, then find a corresponding, and we say this word like this, orthonormal set. So we don't know what that means either, so we better go ahead and look at some definitions. Now, all these definitions I show you are on the definition sheet that's located on the main page of my website. Definition. If a vector has norm or length of 1, then it is called a unit vector. So unit vectors have length 1. Theorem. If you have a vector v and it's non-zero in an inner product space v, then the vector u, which is v divided by its length, is a unit vector in the direction of v. The process of replacing v with u is called normalization. Okay, so if you've got a vector that's length 7, all you have to do is multiply it by 1 over its length, and then you've got a vector of length 1 which points in the same direction. Okay, and for some of you, you know what this is. Definition. A set of non-zero vectors in an inner product space V is called orthogonal. So now we're talking about orthogonal set of vectors. If every pair of vectors in S is orthogonal. Okay, so you just have to check that every pair is orthogonal. If, in addition, each vector in the set is also a unit vector, then S is called orthonormal. Okay, so let's go back to our examples and do the problems. Now there will be 3 more theorems, but they're really not going to matter too much unless if you're a math person or a technical person who's enjoying the class, then we'll take a look at 3 more theorems after this. So what are we to do? We are to figure out if this is an orthogonal set. Now, these look like vectors in R4. Okay, so R4 is the vector space for both of these examples. But something's missing. They did not define what the inner product was. So when they do not define the inner product, then we take the inner product to be the standard one for R4, which is dot product. Okay. Now if we wanted a non-standard inner product, we would have defined it. So we're just going to dot the first 2 vectors together. When I dot the first 2 vectors together, let's go ahead and just say this is the dot product right here. What do I end up getting? Okay, so here I'll use 2 pens to illustrate. 1 plus 2, so we're at 3 now, minus 3 plus 0. That has a dot product of 0. So it's looking good. The deal is for this set to be an orthogonal set, all the pairwise dot products have to be 0. Let's try out the first one and the last one. Okay, here it goes. 0 plus 2 plus 0 minus 2. So this one's 0 as well. Now, I've worked for the federal government, so at this point, sometimes you would go, oh, it's Friday, it's good enough. But you really don't want to have that attitude. You want to check all the pairs. And there's one pair we didn't check. It's this one right here. So let's do the dot product of those guys. So I end up getting 0 plus 1 plus 0 plus 0. That one has a dot product of 1. So guess what? The answer to this problem is no. This set is not orthogonal. So we say no. Because the second part is a follow-up of if yes. So we had no, we're done. Okay, let's take a look at this one here. Notice the first two vectors are the same. So we can say, hey, the dot product here is 0. Okay. Because we did that up there. It's this vector that got swapped out. Okay, so now what I'm going to do is I'm going to do the dot product here. 2 minus 2. No, I can't actually do arithmetic. Let's try that again. 2 minus 4 plus 0 plus 2. So 2 minus 4 plus 2. Hey, that's 0. Okay. And then let's do this one. This is going to be 2 minus 2, and then 0 and 0. So guess what? This is a yes. That is an orthogonal set. Now, since we have a yes, we have to find a corresponding orthonormal set. Now, how am I going to do that? This is not an orthonormal set right here. Okay, so let me just illustrate that. So I'll just say this is orthogonal set, but it's not an orthonormal. Why not? Because look at the length of this vector. Is it length 1? This vector has length. Let's see if we could do the length of this. This is 1 plus 4 plus 1 plus 4. So we don't want to say this vector has length 10. It has length root 10. Okay, so let's put this vector right here. So this has length root 10. To make it so it has length 1 but pointing in the same direction, you go 1 over root 10. Now that vector has length 1. And what was that called again? That was called normalization. We just normalized that vector. So this vector has length 1. Why don't we write these three vectors and normalize each of them, and then we will have a corresponding orthonormal set. So we just have to figure out the length of this one now. So this is square each of these, because you're taking the dot product of this in itself and then doing the square root. So this is 1 plus 1 plus 9. That gives me 11. So the length of this vector here is not 11, it is root 11. So I'm going to get 1 over root 11 times this vector, 1, 1, 3, 0. And then the last one here, it has length, let's see, 4 plus 4, that's 8, plus 0 plus 1, that's 9. So it doesn't have length 9, it has length square root 9. But square root 9 is 3, so this vector has length 3. So I'm going to go 1 over 3 times this vector, 2, negative 2, 0, 1. And now this vector here has length 1. And so each of these vectors have length 1. They're pointing in the same direction as those vectors. And if you do dot product, you know, like we did up here with this one, you'll end up getting 0 because you're really not changing the direction. So these will give you dot product 0. You can normalize. And so that is the answer that they want. They want yes, and then they'll say, look at this. You've now got, this is orthogonal set. I don't like that pen. Let's see if I have another pen. And then it's also an orthonormal set. And so that's what we have. So this completes section 5.2. I'm going to show you some theorems. So here are some theorems here. If S is an orthogonal set, so not orthonormal, just an orthogonal set of non-zero vectors in an inner product space V, then S is independent. Okay, so there's a connection between an orthogonal set and being independent, and that theorem says that. Now some of you are like, well, I don't really care about that theorem. That's alright, you don't have to care. Next theorem. If V is an inner product space with dimension n, then any orthogonal set of n vectors is a basis. Okay? You probably used the last theorem to prove this theorem. We're not doing proofs of theorems in here. And then here's something else, and we probably won't even use this in our homework. V is an inner product space with an orthonormal basis. V1, V2, V3. Okay, we're going to make this vector space V have dimension 3. Let U be a vector. Okay, so sometimes what you want to do is you want to find the component vector, which is a pain because you have to write these guys as linear combination and, you know, maybe do a system of equations. Watch this. The component vector of U relative to B can be found by simply taking the inner product of U and each of these basis vectors, loading them up in a column, and then that gives you the component vector. So it's actually a lot easier to figure out a component vector of U relative to B if your basis is an orthonormal basis. Well, this is just an introduction to linear algebra, and so some of the stuff we won't see, but if you take certain technical classes, it might come back to some of this stuff that we're doing right here, and this would be very useful. But in your homework, you're not really going to be doing this. You're going to be doing that right there. So do your homework. Have a good day. I'll see you in the next video.